Ohad Kimelfeld on covert entanglement generation secrecy.
Sorry. Hi everyone. This is a joint work with Professor Bolot Bash and Professor Uzi Pereg, who are both sitting here. And this work is about covert entanglement generation and secrecy. So let's begin with some motivation. As you may know, privacy is a fundamental aspect of communication. Secrecy guarantees that the transmitted information remains inaccessible to an adversary, which means that if the adversary receives any information, it doesn't depend on the message that was sent. However, covertness is fundamentally different. It ensures that the transmission itself remains undetectable. Okay, let's consider the following setting in which Alice and Bob try to generate entanglement via a quantum channel. And in this work, we show that this can be performed covertly, which means that without being detected by Willy, which is our adversary, and in covert communication, we call him the warden. Furthermore, to prove this, we achieve another meaningful result in which we show that classical communication can be performed both covertly and secretly via classical quantum channel. Okay, but covertness comes at the cost of the square root law, the SRL, allowing reliable covert transmission of only the order of square root of n, where n is the block length of bits or qubits or e-bits, depends on the model, in n-channel uses. And as you can see, there's been an extensive previous work about this topic from classical channels, classical quantum channels and quantum channels, both for continuous variables, bosonic channels, and for discrete variables. Okay. Another topic that we're interested in is the entanglement generation, which is, as you know, is a fundamental process in quantum information science, from computing, communication, cryptography, and so on. Working? Yeah. Okay. Oh, this is much better. Thank you. Okay. So, much better. So, entanglement generation, you may all know, is a fundamental process in quantum information science. And it turns out that specifically, entanglement can enhance or boost the performance of covert communication, enabling the order of square root of n times log n of information bits. Okay, our main contributions in this work, first, as I told before, covert secrecy. We first established a single letter formula for the covert capacity for sending classical information under a secrecy constraint. And you may think that if we achieve covertness, why do we also need secrecy? It sounds a little bit redundant. But since covertness is typically defined in a statistical sense, achieving both covertness and secrecy makes privacy more robust. So this is not merely just an auxiliary result, it's also interesting and meaningful to achieve both covertness and secrecy. And we achieved that the same capacity, the capacity for covert and secrecy is the same as for the capacity without secrecy. But we need a larger key. And then we establish a single letter formula for the covert capacity for entanglement generation or generating EPR pairs. And it turns out that the same capacity for entanglement generation is equal to the capacity with the covert capacity with secrecy, and it equals to the capacity, the classical capacity without secrecy. So we achieve this nice relation. Okay, some definition and properties. A quantum channel is a completely positive trace-preserving map. Every quantum channel has an isometric channel where V is the isometry that maps from the Hilbert space for the system A to the combined Hilbert space for the systems B and W, where W is a system of Willy or Warden. The quantum relative entropy, also known as the divergence between two states, rho and sigma, is defined as this way. But we need also a less common information measure, which is the eta measure. And it is defined this way for spectral decomposition sigma. This way, we define it this way. And some nice properties of the eta measure. First, if rho and sigma commute, then the eta measure is equal to the chi-square divergence. And another useful property that we'll be using a lot is if you consider a Bernoulli alpha with the probability alpha distribution over the ensemble rho and sigma, then for small alpha, we obtain this nice relation between the divergence or the relative entropy and the eta measure. So you can think about it as the eta measure is a kind of a second derivative for the divergence. Okay. About covert communication, which is less familiar. Let's consider, for instance, a classical input x, which can be 0 or 1, where we call x equals 0 the innocent input, which means that there's no transmission or the channel is quiet. Then Willy would like to detect if there was transmission or not, and he performed it by using an hypothesis testing. And our goal is that Willy's probability for error, which is the average between the probability for false alarm and the average, and the probability for misdetection will be as close to 1/2, which means the testing is ineffective or it's like tossing a fair coin. And it turns out that by quantum hypothesis testing and by Pinsker inequality, we can call a code delta covert if the divergence between Willy state when there's transmission and Willy state when there's no transmission is delta small. Okay, so what is the coding scheme to achieve covert communication? We use a sparse coding scheme with only a fraction of alpha n non-zero transmissions, which means that we obtain for Willy the output state, which is the average over the Bernoulli distribution with a probability alpha n, where omega 0 is Willy state corresponding to the inputs to the innocent input 0, and omega 1 corresponds to the input 1. And as we saw earlier, we have this nice property of the divergence and the eta measure, and this way the covert protocols ensures that the divergence for Willy's actual state is approximately equal to the divergence for Willy's desired state or encoded state. And this vanishes for choosing alpha n to be of the order of 1 over square root of n. Okay, let's proceed to covert secrecy. Let's consider secret communication via classical quantum channel. And this is our model. First, Alice and Bob have a pre-shared secret key. Then Alice decides whether to communicate to Bob or not. If she doesn't transmit anything, then the input to the channel P is 0 to the n. Otherwise, she encodes her message M and transmits it via n channel users of the channel P. On the other side, Bob and Willy receive the systems Bn and Wn respectively, Bob tries to decode and estimate the original message M, and Willy performs two things. First, he tries to test whether there was transmission or not via hypothesis testing, and if he does notice that there was transmission, he tries to decode and estimate the original message. Okay, so let sigma x and omega x denote Bob and Willy's reduced states, respectively. Again, for a given input x, which can be 0 or 1, where again x equals 0 is our innocent input. Okay, so Alice would like to send her classical message both covertly and secretly. Then secrecy code satisfies three requirements. The first one is Bob's decoding reliability. Well, the decoding reliability, where Bob's probability for decoding error is epsilon small. The covariance criterion, again, the divergence of Willy state when there's transmission and Willy state when there's no transmission is delta curve small. And for secrecy, we take the trace distance between Willy state that depends on the message M and some state that doesn't depend on the message M, which should be delta sec small. And we take it further by taking the semantic secrecy, which is the maximal trace distance over the message. And because in covert setting the number of information bits is of the order of square root of n, the Shannon capacity is equal to 0 here, because Shannon capacity is normalized by n and not by square root of n. So we need to redefine the rate, the covert secrecy rate, by the number of information bits divided by the square root of n times the covertness bound, delta curve. Okay, some definitions. A covert secrecy rate, LS, is achievable if for every epsilon delta curve and delta sec and sufficiently large n, there exists a code for covert and secret classical communication. And the covert secrecy capacity, CS, is the supremum of all achievable rates. Okay. Now, before we get into the main result, we take two main assumptions, two important assumptions. The first one is that Willy's test is not trivial. Mathematically, it can be described as the support of omega 1, which is Willy's state corresponding to the input 1, is a subset of the support of omega 0, which is Willy's state for the innocent input 0, and that these two states are not equal. This eliminates cases where both Willy can detect non-zero transmission with a high probability, and that Willy could never detect transmission. Another important assumption is that Bob would not have an unfair advantage over Willy, which means mathematically, again, the support of sigma 1, which is Bob's state, corresponding to the input 1, will be a subset of the support of sigma 0. And this guarantees that Bob cannot detect a non-zero transmission with high certainty. Sorry. And now we reach to the first main result. The covert secrecy capacity is given by this single letter formula, where it's the divergence between Bob states divided by the square root of the eta measure of Willy states times 1/2, provided the assumptions we described before hold. And for comparison, as we mentioned before, the covert capacity without secrecy by Bullock et al., which was presented here a year ago, is given by the same formula. But in this case, without secrecy, we need a smaller key. than our result with secrecy. Okay, so we show this here. Code communication without secrecy requires a key rate of this size, which is, here you can see the difference between the divergence of Willis states and the divergence of Bob states. And in our case, with secrecy, we need a key size or key rate of this size, which is bigger than this key rate. And because of this, we divide it into two cases. The less interesting case is where the divergence of Bob states is no greater than the divergence of Willis states, where secrecy can be achieved by a one-time pad encryption because the key is large enough. The more interesting case is the opposite case, where the key is shorter than the message and we need a more elaborate coding scheme. So what do we do? First, we perform a rate splitting. We consider a message consists of two components, M1 and M2. Then we select code words C of M1 and M2, each IID Bernoulli with probability alpha n, where if you recall, alpha n is the number of the fraction of non-zero transmissions. The encoder is given the message M1 and M2, we transmit the code word, and the decoder time is the same decoding map as without secrecy. Okay, the error and covariance derivations follow the previous results without secrecy by Bullock et al. But to ensure secrecy, we combine both OTP and binning techniques, and this follows Bloch's approach from his paper in 2016. So first, we perform one-time pad on M2, and this ensures, this is why the key is equal, the key size is equal to the M2 size, and this, of course, ensures perfect secrecy for M2. Then we perform binning. We divide the random code into M1 bins, each of size M2 or K, which is our key size. And we're using this to establish secrecy by applying the quantum channel resolvability. The converse is pretty immediate because the capacity without secrecy is an upper bound. And finally, for the next step, to establish entanglement generation or covert entanglement generation, we bound on the maximum rather than the message average error criteria. Okay. Now, let's consider entanglement generation via quantum channel N from A to B with a thin spring dilation U, which we add the system W. An important assumption here is that Willy holds W, which is the entire receiver's environment, or Bob's environment. And this is our scheme, our model. It looks pretty similar to the previous model for a classical quantum channel with secrecy, but now it's fully quantum. Again, Alice and Bob have a pre-shared secret key, but now Alice generates locally a maximally integrated state capital Phi between the systems M and R. R is the resource. And again, she decides whether to perform the task of entanglement generation or not. If she doesn't perform the task, the input to the channel is the state 0 to the tensor n. Otherwise, she encodes the system M and transmits it via n-channel uses of the channel U. Again, on the other side, Bob and Willy receive Bn and Wn respectively. Bob tries to decode the system such that he will receive on his end the original state, or approximately the original state capital Phi. And Willy perform hypothesis testing to know whether there was an attempt to create entanglement or not. Okay, so Alice wants to establish entanglement of dimension T with Bob and covertly, of course. And similarly, let sigma x and omega x denote Bob with really reduced states, respectively, but now for the orthonormal basis X, where X again can be 0 or 1, where 0 again is the innocent input. So a code for covert entanglement generation satisfies now two conditions. The first one is the decoding reliability for Bob, but now we use the fidelity between the shared state between Bob and the resource and the original maximally tagged state, capital Phi. And of course, we want it to be as close to 1. And the covertness criterion is similar to the previous model. And similarly, we define the covert entanglement generation rate as the number of EPR pairs divided by the square root of n, again, instead of n, times the covertness criterion, or covertness bound. Again, definitions, covert entanglement generation rate, LEG, is achievable if for every epsilon delta and sufficiently large n, there exists a code for covert entanglement generation. And again, the capacity, the covert entanglement generation capacity, is the supremum of all achievable rates. And we take the same assumptions as in the previous model for covert secrecy. Now, our main theorem, the covert entanglement generation capacity is given by this formula, which, as you recall, is exactly equal to the covert secrecy capacity, which is also equal to the covert capacity without secrecy constraint. And again, provided that our assumptions hold. And before we go to our proof, let's see in a little example the excitation channel, which is the opposite process for the well-known amplitude damping channel, where with probability gamma, the ground state 0 gets excited to the state 1. And the covert entanglement generation for this channel, before that, the channel can be represented with this Krauss representation. And the covert entanglement generation capacity is given by this formula, which is, of course, parameter of the probability gamma. And as you can see in the plot below, when gamma goes to 0, covertness becomes trivial because now the number of EPR pairs is linear in n. And as you recall, we normalize the capacity or the rate by square root of n. So this is why it goes to infinity. And for gamma equals 0, reliable communication is impossible because Bob states are equal. Okay, so a little proof outline. For achievability, we construct the entanglement generation code from the classical secrecy code based on the Vetax approach from his seminal paper in 2005. So the code conversion that we apply is that for the classical codebook X to the n, where M and K are the message and the key. For this codebook, we define the following: the classical quantum channel P for the classical input X is equal to the quantum channel for the pure input X. Again, for X can be 0, 1. And Alice creates a quantum codebook, phi of m, with the quantum code words that looks like this way, which is kind of a Fourier transform over the basis x to the n of m and k, which is constructed from this classical quantum codebook, or classical codebook x to the n. This is a result of the Vetax approach. And based on the maximal error and semantic secrecy that we achieved for the secrecy code, we obtained that the shared state between the resource, Bob, And Willy is approximately decoupled from Willy, so Bob can approximately decode the original maximally integrated state, capital Phi. And we show covariance holds. This is the last part of the achievability proof. We show covariance holds using properties from the secrecy code and continuity properties of the quantum relative entropy. And finally, covariance is also pretty straightforward because the entanglement generation capacity is bounded from above by the classical capacity without secrecy. Okay, to summarize, we showed that approximately square root of n times the capacity for entanglement generation of EPR pairs can be generated covertly. This is our main result. Our second main result is that we determine the covert secrecy capacity, which are equal. And both of them are equal to the rate or capacity for classical formation without secrecy. But in our scheme, we need a larger key. And although our key has a limited rate, its optimality still is unknown. And for future work, we would like to first investigate the non-isometric case. If you recall, Willy holds entire receiver's environment. If we would like to analyze the scenario where Willy does not hold the entire environment, which means there's Willy and environment that we should protect from applied secrecy. Another thing is that in scenarios where Bob has an unfair advantage, we know from classical quantum channels that the key that we need is basically 0. So what about the covert entanglement generation setting? Do we need a key or the key is 0? And last thing, because now we have a capacity formula for covert entanglement generation, and we have from previous works, and also our work with secrecy, we have a classical communication, also capacity for classical communication with covertness. We'd like to check the feasibility and efficiency of covert quantum teleportation. Thank you very much for listening.
Thanks so much. Questions?
Thanks for a nice talk. I mean, this might be a bit naive, but is it sensible to talk about the one-shot version of this?
The what?
A one-shot version of this?
Which version? Sorry?
One shot. Like if you fix n equal to 1, and then you talk that, okay, I transmit 0 with some probability, 1 with some probability, and then try and formulate like this kind of problem.
Sorry, can you repeat again, because I didn't understand.
Yeah, so like I want to fix n equal to 1.
Any quarter?
N is equal to 1. So I just want one transmission.
Yeah.
I'll transmit a 0 with some probability and 1 with some probability.
Yeah.
And then like, can we talk about the covert secret capacity of a channel?
It's a good question. Basically, the proof works for large n, where we get the bounds when n goes to infinity. And there's another thing that for covertness, we need, in all the proofs, at least that I know of, we need that the message will have a uniform distribution, which means we need to average over the message and the key, but most importantly the message. So different type of distributions, it's very interesting, but at least in this work and other works in covert communication, we need the average, the uniform distribution. I hope I answer your questions.
Yeah. And like, can something change if I give side information to, let's say, Bob? Like, how does the capacity change, like do you have any
If
intuition on it?
if I give him side information, we didn't think of it. I don't know. I don't know. We need to think about it. Good.
Can comment?
Yeah.
I don't know of any work on one-shot covert communication, but I think it's not obvious, at least to me, it's not obvious whether the scale will remain square root of n.
Yes, yes.
Whether you can actually show, or we know how to show that it's still the scale of n, or any scale.
Right.
Of course, you would need, in one shot, you say I have epsilon error, and
Yes, yes.
you will also say delta coverateness, right? You
Yes.
have to, so it will depend on two parameters. And there are some work, at least in the classical case, on side information. There are works about this, and it does improve the results. And in particular, in some cases, you can get rid of the key. Because you need it in covert communication, at least under those assumptions, you need a key.
Yes.
And with side information, in some cases, you can get rid of it.
Okay. Thanks.
There's a follow-up comment by Bula.
Yeah, regarding the one-shot version of this, there's the classical quantum works on the bosonic channel, which have the second-order results, basically fairly as what we expect. But it is an interesting question that we should think about. Thanks.
Any other questions?
Thanks for the talk. So throughout your work, you assumed that the warden had access to the entire channel environment. Do you know what happens if, for example, the warden only has access to part of the environment? Can you make use of this?
Yeah, so this is a good question. This is exactly the first point here for future work, which we are currently working on. And this is a little bit more complicated because now, if you recall, we have assumptions on Will states and Bob states and their support. But now, if there's also environment, we don't really need to assume that these conditions hold for the environment. So it's a little bit more trickier, and we're currently working on it.
Do you have a conjecture of whether it will improve the rates, for example, or?
No, but we think that probably the rate will be the same, but the key will be a little bit higher. Yeah, we need a larger key.
It should improve things, right? Like if the warden has access to everything, then it's worse, right?
Yeah. In the formulas, you will have, instead of the warden states, you will have the environment, or the
combined
environment, including both Willy and the rest. So yes, it does improve.
Okay. Thanks.
Quick one.
Thanks for the nice talk. I had a really basic question. So you have this delta in the definition of the rate. I've never seen that sort of thing before. Is that?
Yeah.
Should I have an intuition for that?
No, this is a very good question that we were debating about it yesterday. It's okay. Few things. First is the standard definition of covert rate, but intuitively, it's mathematically it works better if we plug it in the definition. And intuitively, and Bulat and Uzi maybe can help me, but intuitively it balances because on the one side you have how covertness you want to achieve, and on the other side, how many bits or qubits do you want to send. So it balances the trade-off between these two edges.
Okay, thank you.
Let's maybe take the last questions offline and thank Ohad again. Thanks.
Thank you very much.